Hello, my name's Paula Carey. I'm the founding director of a company called Carbonate Systems and also the Chief Technical Officer. I'd like to talk today about the use of accelerated carbonation to valorize incinerator residues, particularly in contrast to a lot of the other talks over the next 2 days, looking at the air pollution control residues rather than incinerator bottom ash. So I want to introduce the various options for the treatment of air pollution control residues. I'd like to explain a little bit about accelerated carbonation technology for those who are not familiar with it, look at how Carbonate Systems has commercialized the technology, look at the properties of the aggregate product and the use of that aggregate and what the drivers are for the treatment process. So first of all, an introduction to the air pollution control residues. I'm sure many of you know, but APCR is generated as a result of the addition of lime to the flue gas system to capture the acids in the flue gas generated by the incinerator. And then the lime, alongside the fine particulates in the gas or the fly ashes, are captured in filter bags, and it's this residue from the filter bags that we have developed a treatment for. Compared with bottom ash, APCR is produced in much smaller quantities. So for each ton of waste burnt, between 15 and 40 kilos of APCR is produced. Unfortunately, it's classified as a hazardous waste, primarily because of the high pH as a result of the lime, but also because of its content of heavy metals, principally lead, nickel or zinc. And because of its hazardous nature, across the world, the majority of APCR is landfilled. That invokes quite a large cost. In Northern Europe, particularly, including the UK, disposal costs or the management costs for APCR are in the region of 120 euros per tonne. And the majority is still destined for disposal either at landfill or used as or stored in salt mines, as shown in the picture here, or used as an engineering fill in salt mines. There are several companies working on or trying to commercial alternative management solutions for the APCR. Of these in the UK, 3 have obtained end of waste approval from the regulators. So this is using the APCR as a product rather than as a waste. So the examples of those is where it's being used as a supplementary cementitious material, or an SEM. In Scotland, there's a process where the APCR combined with fly ash and boiler ash is used as a replacement for PFA in cement. A company in Wales is washing APCR for then inclusion into large concrete blocks. Both these solutions presumably required the removal of the chloride, and certainly the system in Wales involves washing the APCR before it's included in the concrete blocks. So you have 2 problems. One is drying of the washed APCR before it can be used, and also disposal of the wash water that is alkaline and contaminated with heavy metals as well as chlorides. Our approach is to use the air pollution control residues to manufacture an aggregate for use principally in concrete, using carbon dioxide as an ingredient in the process. So to think about what accelerated carbonation technology is, it's the reaction of calcium and magnesium minerals, principally oxides, hydroxides, and silicates, that occur in a range of thermal residues, such as the incinerator ashes. So both the fly ashes, the boiler ashes, the APCR and bottom ashes contain these phases. And if the conditions are right, these minerals will react with CO2 and you can manage them to form carbonates. So in the simplest form, if you take calcium oxide and you add CO2 to it, you get calcium carbonate. And the formation of the carbonate reduces the pH of the system. The pH of calcium carbonate is around 9, and it stabilizes some of the problematic heavy metals within the residues because they have a lower solubility at a pH of around 9. And of course, the CO2 is permanently captured as calcium carbonate, as illustrated here by the White Cliffs of Dover or the Seven Sisters, where the natural process of carbonation has taken place, where calcium and magnesium salts have reacted with CO2 and formed calcium carbonate, which has lasted for millennia. So for accelerated carbonation, there are two main process conditions, and a whole range of different companies and universities have been looking at carbonation at a variety of conditions. Principally, you can divide them into wet and dry carbonation. So wet carbonation is where the water to solid ratio is in excess of 1:1, and you have alkaline waters which effectively solubilize the calcium ions or the magnesium ions, and you get precipitation of the carbonate within the water. So the calcium carbonate or magnesium carbonates form relatively pure compounds away from the solids where the calcium and magnesium ions started. And then there's the technique that Carbonate Systems uses, which is called semi-dry or thin film carbonation, where the water-solid ratio is less than 1:1, and the carbonate actually nucleates on the grains of the residue or replaces the grains, and the formation of carbonate actually binds the original or the modified grains together. This reaction can occur at atmospheric temperatures and pressures, or at a range of elevated temperatures and pressures up to supercritical CO2 conditions. But at Carbonate Systems, we try and we possibly sacrifice a little bit of the CO2 uptake of the materials, but that's balanced by the saving of energy by using atmospheric temperatures and pressures rather than elevated temperatures and pressures. Alongside incinerator bottom ashes, where it's common to leave the materials to weather, we can look very briefly at the difference between weathering and accelerated carbonation of materials such as air pollution control residues. On the left-hand side, you can see the effect of carbonation over a period of 70 hours. And you can see that there's a very rapid drop of pH in the first hour or so. Whereas with weathering, the pH varies a bit, and actually even over 12 months left out in just to weather, you don't get much of a pH drop. But you do see a little bit of carbonation, but the actual carbonate phases, the polymorphs of the calcite or aragonite or I can't remember the third polymorph of vaterite, that's it. The vaterite, you get different ratios of those, whether you accelerate carbonate or whether you weather the material. So just thinking about how Carbonate Systems have developed the technology, and it's a classic spin out from a university research department. And the team at the originally at Imperial College and then at the University of Greenwich have been working on accelerated carbonation since the early 1990s. In the 2000s, we did a lot of work with the Environment Agency in England to develop solutions for the treatment of bottom ash and APCR that involved looking at the contrast between accelerated carbonation and weathering, and showed the Environment Agency that accelerated carbonation was a reasonable solution for treatment of these ashes. As a result of that research and other projects that we had at Greenwich, the company Carbonate Systems was founded in 2006 under license from the University of Greenwich for the technology. And between 2006 and 2010, we did a lot of lab scale trials and development so that we had the confidence in 2010 to form a second company with a license to treat APCR in the UK. The APCR treatment plants in the UK were built on the basis of a number of pilot scale trials funded by government grants and by the Shell Springboard Award to Carbonate Systems. And after the success of that, the first air pollution control treatment plant was commissioned in 2012. And the aggregate has been in use since then, principally in concrete blocks. In the process, we call it a three-stage process. The APCR is initially mixed with water and carbonated prior to mixing with further binders and fillers in order to form the pelletized carbonated product. So CO2 goes in at both stage 1 and also in stage 3 in the pelletizer, so that the binder is also carbonated to produce the finished aggregate. So in the UK now there are 3 commercial plants, treatment plants, each with a capacity of up to 40,000 tonnes a year of APCR that use pure CO2. So it's captured from processes such as fertilizer manufacture or breweries, but principally fertilizer, and delivered in a tanker where it's kept refrigerated and then vaporized as it goes into the mixers. But of course, there's a shortage of CO2 in the UK. The fertilizer factories are affected by the cost of oil and gas, and so there's limited capacity and there's premium price on the CO2. So Carbonate Systems back in 2018 decided that the best route was actually to use CO2 extracted directly from flue gas. And we undertook a trial in Ontario, funded by the Ontario Centre of Excellence, and demonstrated that this was possible using concentrations of CO2 at something above 10% by volume in these typical flue gases from either cement works or an energy from waste plant. The package, the containerized system, comes in 2 40-foot shipping containers. So there is minimum disruption to a site when you install one of our plants, and it plugs directly into the flue stack. So extracts flue gas from the flue stack, passes that through our mixer, and then any remaining flue gas is returned to the flue stack. So there are no emissions. And illustrated here is a plant that we used to demonstrate the technology at an energy from waste plant in the Netherlands, not actually using flue gas directly there because the site already captures its CO2 for use in greenhouses. And on the right here, we have a photograph of our plant at a cement works in the south of France at the VCAT Cement Group's site at Montpellier, where that is successfully producing aggregate from the cement bypass dusts that are a residue from the cement manufacture. So the properties of the aggregate are similar to those of an expanded clay aggregate, with the important distinction that it has captured CO2 up to 15% by weight of CO2 in the makeup of the aggregate. They have comparable strengths, or the strength of the APCR-based aggregate is stronger than that of expanded clay. But the aggregate is probably slightly denser than typical expanded clays, although they do vary from the 350 kilograms per cubic meter stated here up to 800 or 900. The water absorption is similar or less, and so they can be used in very similar applications and are tested to EN 13055, the standard for lightweight aggregate. And as such, the aggregate can be used in a range of applications to produce low carbon building materials. Principally, the material goes into concrete blocks, and there's a history of use since 2012 into these typical aggregate medium dense or dense blocks. The material can be used in ready-mix concrete. There's examples where it's been used in asphalt for footpaths or cycleways. It makes an ideal material for pipe bedding because of its round shape. The utility pipes can be bedded quite readily into the material. And we've recently demonstrated its use very successfully in a low carbon flooring system, where the material has been used in conjunction with basalt-based reinforcements rather than steel. And as you can see, you can get a beautiful smooth surface through concrete containing the carbonated aggregate. So there are a range of drivers for the system, and we all know that these ashes are a problematic waste stream from energy from waste, or many of the other hard to abate industries such as steel or cement, paper, or energy from waste. They produce these fine-grained residues and the CO2. So these are liabilities, and carbonate systems and accelerated carbonation technology changes those liabilities into assets, so that you avoid those high landfill costs. You can produce a low carbon building material with value, and you can also get credits for value out of the carbon removals. So we have a 10 years track history of the manufacture of aggregate from APCR and its use in principally concrete blocks. There is an opportunity to treat particularly the fines from incinerator bottom ash rather than leaving them out to weather. You can use an aggregation process to convert the fines into a coarser aggregate. We can directly capture the CO2 from the flue gas without need to purify it, and none of the expense of having to transport the CO2. And we can successfully use the aggregate in a range of different low carbon applications. Thank you.